In this presentation, I will talk about my research and development process in order to build a solution for the 3D segmentation of objects in a video feed and in real time. The developed solution aims to be integrated in a larger computer vision system, and the general idea of the system is to create a voxel grid representation of a certain scene. This scene in particular is filmed by a Z stereo camera and is composed by one or more operators, a robotic arm, and a set of small objects. It's easy to construct a voxel grid from a point cloud representation, but these are often under-optimized since the size of every voxel in the grid is the same and the voxels themselves are unlabeled. The innovative part of the vision system is to tailor the size of the voxels according to the size of the objects it's trying to represent and also label them. So you can imagine when you have a person and a screw in the same scene, you can represent the screw with a single voxel that fits it perfectly, but also in the same exact grid use bigger voxels to represent the person. And with labeled voxels, you can construct better path planning algorithms and make the whole system more secure for human-robot collaboration. So what exactly did my solution need to accomplish? In the simplest form, given the inputs of a Z camera, it needed to output the 3D point cloud for every object in the scene, along with the classification. There were a few select requirements that guided my research. First, the system needs to process video frames in real time. In this context, this means at least 25 frames per second, ideally 30, which means that the processing time for each frame needs to be no more than 40 milliseconds. The second requirement is that the segmentation doesn't have to be perfect. We don't need the tightest fit we can get. In fact, the more relaxed and wider the segmentation, the more secure any path planning is. To these two core requirements, I added a few of my own to try and create an optimal system. First of all, I wanted to reduce and even eliminate any GPU processing. This is due to the fact that most factory environments don't have high-powered GPUs, and even the ones that do have GPUs, it's mostly shared between applications and its use is limited. Along with this, I also wanted to reduce the memory imprint of the system. So if I did use any kind of machine learning model, I wanted it to be a light model. Finally, it was important to classify the objects without using any kind of object classifier based on machine learning. Because as most of you will know, object classifiers need to be trained to the specific application they will be used in, which means that every time a new class of object is introduced into the environment, the model needs to be retrained to be able to classify it. This is where the need for class-agnostic methods came from. And basically, to achieve this, the system can receive a couple of inputs to help it classify objects after segmentation, such as a set of points belonging to the persons in the image, the coordinates of the base and the end effector of the robotic arm, and for the objects, their size and color, and possibly even a model of their shape. With these requirements in mind, I started searching for state-of-the-art methods to achieve the results that I wanted. I would like to start by talking about what didn't work and how I arrived at a solution that does work. When I thought about 3D point cloud segmentation, my first idea was, of course, to search for segmentation methods that worked on point clouds from whole images. The main traditional methods of point cloud segmentation can be seen in this diagram. One of the biggest issues with these methods is how complex the data is. Collections of thousands of points in 3D space are of course way more complex than values on a 2D grid, and as such the computational power needed to work with point cloud data is much higher than with RGB images. And even with that computational power and the fact that neural networks such as PointNet have been developed to work on point cloud data, these models can't achieve inference in real time. So deep learning on point clouds was not an option for this application. The initial idea was then to reduce the amount of points the system would have to deal with. To achieve this, the objects would be located in the RGB image using bounding boxes, and the point cloud data would be extracted from that bounding box region, and traditional point cloud segmentation methods would be applied according to the type of object. In the case of a person, the set of points that belong to them would be used as seeds for a region growing algorithm. For the robotic arm, a model-based segmentation approach would be used. And for the objects, since they are small and simple things like cubes, balls, and screws, the extracted point cloud from the bounding box could serve as the segmentation result itself. After testing a few region growing and model-based algorithms, the results weren't good enough. The region growing algorithms achieved poor speed, close to 250 milliseconds per frame, and the model-based algorithms were fast, however they didn't work for all viewpoints and positions of the robotic arm. To achieve better results in processing speeds, point clouds are usually turned into voxel grids, thereby reducing the amount of data points that need to be processed. However, it's redundant to use voxelization as a pre-processing step in a system that is supposed to aid voxelization. So for those reasons, point cloud segmentation methods were discarded and I moved on to a different approach. Similar to the first one, this approach also detects objects in an RGB image using bounding boxes. However, the segmentation is also done on the 2D image. This results in a pixel level mask for each object, and the locations of the pixels in the mask are used to extract the corresponding 3D point cloud. For the detection stage, the idea was to use a class-agnostic bounding box detector. This means that the detector should output bounding box predictions without a class label. However, most of the state-of-the-art detectors right now are all class-aware, so they are trained with class labels. This means that if I want to implement one of these detectors, I have to do one of two things. Either train the whole model with a dataset composed of only two classes, background and object, which has obvious downsides because the class prediction will have to learn the features of all types of objects, from humans to medium objects to small objects, and simple and complex features, and this would likely result in very poor precision. The other way offers better results, but it requires breaking up these models and messing with the neural network structures. The good news is that the top two deep learning models for object detection, YOLO and SSD, use a similar modular structure. They are composed of a bounding box predictor and then an object classifier applied to the prediction. So ideally, we can only use the bounding box predictor and remove the classifier portion of the network. This also has the benefit of reducing processing time. Now, my first option was to use YOLO, since it already had a lot of optimized models for processing speed. Most notably, Tiny YOLO achieved 144 FPS on a Titan X GPU. However, when translating that to CPU performance, it rapidly decreases to about 2 FPS, which is not enough for real-time applications. I tried to apply some optimizations, try and get better speeds, and I also saw this as a learning opportunity. I tried to apply some optimizations, try and get better speeds, and I also saw this as a learning opportunity, since I had never optimized a neural network like this. The obvious first route when trying to increase the processing speed of a bunch of data is obviously to make it smaller. Less data leads to less calculations, so the first step was to reduce the resolution of the image to 320 by 320. This had marginal improvement, which didn't really increase the FPS and decrease the accuracy. After some research, I came across a paper which tried to optimize the model by reducing some of the convolutional layers with 3x3 filters to 1x1 filters, followed by a single convolutional layer with 3x3 filters. It also downsampled the image every 3 convolutional layers instead of after every layer. This showed improvements, and it actually increased the FPS to 14 on a CPU. This is an incredible result, however, it still wasn't good enough for this application. I then discovered that SSD had a couple of implementations optimized to run on mobile applications. SSD uses a type of network called multibox for its bounding box predictions. This network was developed by Google, and it outputs accurate bounding boxes for objects in the image. This network suffered some changes to make it suitable for low-power devices like phones and Raspberry Pis, resulting in what is known as Mobilenet. Mobilenet shows great results running only on low-power CPUs. For example, SSD with a Mobilenet predictor can achieve 45 FPS on images with 320 by 320 resolution and about 25 FPS on 640 by 640 images. And the accuracy is also very good for this particular application where we don't need incredibly tight bounding boxes. Now that the bounding box prediction was working in real time, I needed to find a fast and accurate segmentation method to separate the background from the detected object. Initially, I was looking into more deep learning alternatives for segmentation, however, most of them are all class aware, and training a segmentation network is much harder than training an object detector for our specific application, especially if we have to create a dataset ourselves. So in the end, I decided to go for a more traditional segmentation method. I looked at the following 4 methods. As you can see, adaptive thresholding is the fastest segmentation technique. However, it fails when objects overlap each other and when lighting conditions make them blend into the background. For those reasons, it was rejected. The region growing algorithm is more robust than thresholding. However, it takes way too much time to run, and it doesn't work in a real-time application. The watershed algorithm is very fast and more accurate than thresholding, however it can result in over-segmentation. This would be a real problem in case of segmenting operators with different colored shirts, so this algorithm was also rejected. And finally, GrabCut was chosen. GrabCut is an extension of the GraphCut segmentation algorithms, which treat images as graphs. GrabCut is usually used to separate background from foreground, and it works in real time. This algorithm is normally used in an interactive manner, where a user provides a bounding box, and the algorithm outputs the segmentation. Here, the role of the user will be taken by our bounding box predictor. Here are 2 results that illustrate the detection stage followed by the GrabCut segmentation. As you can see in the above image, parts of the person behind are included in segmentation due to similar colors between the 2 people. In the image below, there is a better separation of the object and the background, however the segmentation still isn't perfect. So, what are the advantages and disadvantages of the system developed? First, it works in real time, where the major bottleneck is the bounding box predictor, which works at least at 25 FPS. The system also doesn't use any GPU capabilities, and it's entirely capable of running on an average CPU. And when it comes to memory, the neural network is very lightweight since it uses TensorFlow lines, and the rest of the computation is very basic and doesn't consume too much memory. Now for the disadvantages, one of them is the overhead in training time for the implementation of the model. Also, since the methods are class-agnostic, it's difficult to differentiate between the small objects such as balls or cubes because these don't have identifiable sets of points like persons or like the robotic arm. For that reason, with the introduction of a new object, the code needs to be changed to accommodate for that particular object. This isn't as costly as training the neural network again, but it is a downside. Also, due to the nature of the GrabCut algorithm, occlusion and lighting conditions can affect segmentation results, as seen in the previous slide.